this is an equation review. So basically making an equation sheet for algebra-based physics first semester. So if you're not familiar with this is at the college level. At the college level, there's two kinds of introductory physics. There's one that uses calculus and the one that doesn't. So I'm going to use make an equation sheet for the one that does not use calculus. So it's only algebra-based. Now, for me, this is the book. This John Batista, 5th edition college physics. Really, there's not a lot of difference between the different books. They may write some things a little bit differently, but they're all pretty much the same. And so then I drew a couple pictures here: inclined plane, projectile motion, orbital motion. So let's just go ahead and start. What I want to do is start a single equation sheet, and then if I need to describe something, I'll do it right like that. This particular book starts off with forces, which you don't have to do, but it starts off with vector forces in 2 dimensions and shows that the net force is 0. What can you do with that? So I guess the very first thing is the idea about vectors. I wouldn't put this in my equation sheet, but this is important. So suppose I'll try to appear vector. I'm going to try to make it as neat as possible, but I'll end up being messy because I'm doing this live. So if I guess I should start another sheet. So let's draw a vector. A vector is a quantity that represents something in more than one dimension. So let's call that vector A. So we can represent that graphically as this arrow, but really what's important is the component of that vector in the x and y direction. So if I imagine, and I'm not giving a real big long explanation on vectors, I'm just trying to explain the equations. If I imagine that this is composed of 2 vectors in the x and y direction, then the magnitude of this x component and the magnitude of this y component and the magnitude of that are important, along with that angle theta. So if this is a right triangle, it is, because x and y in direction are in the same direction, or in a perpendicular direction, then I can say AY is a sine theta, AX is a cosine theta. Because remember, sine is opposite over adjacent, cosine is adjacent over, it's early. I just said that wrong. The sine is opposite over adjacent. Cosine is, I did it again, arg. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So that's how you get these two things. Now you do have to be careful about the sign. If I have a vector pointing back this way, then make sure that its x component is negative, but just make sure that happens. Then also, if I have the x components, then I can say the magnitude of the vector A, which we write like this, is the square root of ax squared plus ay squared. If you want to find the angle, you can say the tangent of theta is going to be opposite over adjacent, which is ay over ax. Because those are your main vector equations. Now there is also, I'm going to put it on there, a unit vector. A unit vector A would call A hat. That's the vector A divided by the magnitude of A. And why would you do that? This is a way to make a scalar value a vector. And so I'm going to include this in some of my calculations, in some of my equations. So up here for vectors, I'm going to put AX equals A cosine theta. Now be very careful. I shouldn't put this on here. I really shouldn't, because this is only true if theta is measured from the x-axis. AY is a sine theta. So these are, I'm going to put a little box around them because it's not always true. But this is true. The magnitude of the vector A is ax squared plus ay squared. Tangent theta is ay, that's a y, over ax. And then finally, the unit vector A is the vector A divided by the magnitude of vector A. Okay, vectors. Now, what we do with vectors is to use them to represent forces. So normally you start off with some special force equations. The most important one is in equilibrium. We write this, F net equals 0. And 0 is a vector. Okay, so down here, I should write the couple ways to write vectors. I can say A is AX, AY, AZ in the X, Y, and Z components. You could write A as the vector A, X, X hat, plus A, Y, Y hat. Then you usually leave the Z off. We don't do very many three-dimensional things. And you could write it like this. A equals AX I hat plus AY J hat. And so, plus a K hat. So those are all equivalent ways of writing vectors. Some people just like to write them different ways. So the 0 vector, 0, is going to be 0x, 0y, 0z. So it is different than the number 0. Okay. And we also write this, sometimes it will be written like this. The sum of the forces is equal to 0. And then since this is a vector equation, sometimes it's easier to write it as two scalar equations. F net x equals 0, F net y equals 0. So this is exactly the same as that. I left off the z because, again, no one ever does z. So for forces in equilibrium, this is the main equation that you use. Then what forces do you have? Okay, so the first thing that we have is gravity. So on the surface of the Earth, the gravitational force, I'll call this Fg, is equal to mg. And I am writing that as a vector, where g is the gravitational field on the surface of the Earth. So g has a value of 0, negative 9.8, 0 newtons per kilogram. Now, sometimes you may need to remember equations. Sometimes you may need to remember constants. I give both of those to my students, but I'm just trying to go over the main things that you need to know. So if I take this gravitational field and multiply mass, I get a force. Now, if you get too far away from the surface of the Earth, then the gravitational force changes. And a lot of books write it like this: Fg equals g m1 m2 over r squared. This says that if you have, and g is a constant 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So if I have two masses separated by a distance r, then the gravitational attractive force between them depends on the product of their masses divided by the distance between their centers squared multiplied by this gravitational constant g. If you're on the surface of the Earth, this is equal to g, mass of the Earth, mass, over the radius of the Earth squared, and then you have to have this r hat to make it a vector, negative. So this is, if I set one of the masses equal to the mass of the Earth and the radius equal to the radius of the Earth, then you get this. And you should try that. Now, what if you need a vector version of this gravitational force? It would look like this. Fg equals negative g m1 m2 over r. I'm going to write it like r squared, right? Because r is a vector from the center of the one object to the center of the other one, so it's a vector, and you have to take the magnitude of that vector to square it. And now you don't have a vector anymore, so you multiply it by r hat. And so a lot of books don't put like this, but it is super important if you want to do more complicated things than just calculate the force. Okay, so the two versions of the gravitational force. Next, we have the friction force. This looks like this. Let's draw a picture. Suppose I have a box on a surface, and I push it with a 1 Newton force going that way, and it doesn't move. Then there has to be a backwards pushing frictional force. So I also have the gravitational force pulling down and the normal force up. And this is 1 Newton x hat. That's a vector. Okay. If I push with 2 newtons and it still doesn't move, then the friction force has to increase also. So if it's at rest, if it's in equilibrium, then these two have to be the same no matter what. So that tells me that this frictional force can take any value. If I take this away and that's 1 Newton pushing back, then the block would accelerate this way, which doesn't happen. Okay, so we get the following expression for the magnitude of the frictional force, and then we call this static friction. It looks like this. F friction static is less than or equal to a coefficient of static friction times the normal force. So the normal force tells you how hard the two surfaces are pushed together. It does not tell you it's not equal to mg. It is in this case. It happens to be the case. But if I push down with the force right here, then in order to prevent the box from moving up and down, the normal force have to increase. If I have a box on an incline, then the normal force is always perpendicular to the surface. So I should put over here n equals question mark as a vector, right? There is no equation for the normal force. It's a force of constraint. It says I'm going to push perpendicular to the surface however much I need to do to prevent that thing from going through the surface. And the same is true while we're talking about tension. Tension does the same thing. It's a force of constraint. There's no one equation for it. This says that a string will pull in the direction of the string and to prevent the string from getting longer. That's all it says. Okay, but this is the friction force. Less than or equal to just means that it can be any value. Mu s, that's the Greek letter mu, sub s, that's the coefficient of static friction. It depends on the two types of surfaces. Now remember, this is the scalar version. This doesn't tell you the vector. The vector for the frictional force is parallel to the surface, perpendicular to the surface. So let's write parallel, and then FF. No, I'm sorry, perpendicular. And FF is parallel to the surface. So these are both interactions between a block and a surface. We also have a kinetic friction force. So once things start to slide, then I can say the kinetic friction force is equal to the coefficient of kinetic friction times the normal force. So this shows that it doesn't depend on how fast you're moving. And these are just models. Okay, but once you start sliding, once the two surfaces are moving relative to each other, then there's a constant magnitude friction force on that. Okay, so those are the really big forces to begin with. You may see this one, Fc, I'll write the scalar version, is K times Q1 times Q2 over R squared. This is the electric force between two objects where K is 9 times 10 to the 9th Newton meters squared per coulomb squared. Okay, it looks a lot like gravity. That's why they include it right there. I'm trying to think of any other special forces. We'll get to some other ones. Let's just go ahead and do the rest of the forces. Another force that you may see, I need my equation, continue my equation sheet. Okay. Oh, that's fine. So another force that you may see, I'm going to write right here. Let's just put forces. The spring force. So if I have a spring and I pull it this way, then the spring's going to pull back that way. And the magnitude of the spring force depends on how much it stretches. So a lot of times you would write the spring force looking like this. I wanted to keep this equation right here. It would look like this. F spring equals Ks. That is a scalar equation. Most books actually write this as negative Ks. I think that's a bad idea. I do not approve of negative Ks because S is not a vector. K is the spring constant. The force is not a vector. So it doesn't really make sense. If you want to write it as a vector, I don't even want to do it. But this, I'm going to do it. The spring force would look like this. Negative K times the length of the vector. The length of the vector is length of the spring is a vector from the beginning of the spring to the end. And I would write that as this, L minus L0 times L hat. That's the best way. And then you do have a negative sign there. So this is the length of the vector. That's the unstretched length of the vector. And that's a unit vector in the direction of the unstretched length. This is super powerful, though. You can model springs in 2 dimensions with this. So it's really kind of cool. Another force is, you may see this one, the air resistance force. If you have an object moving through the air, then you have 1/2 rho a c v squared. That's the magnitude of an object moving through the air. Rho is the density of air. A is the cross-sectional area. C is the drag coefficient, and v is the velocity. I feel like I'm missing another force here. Okay, well, I can't think of it. I have a printed out an equation sheet, but it's not on there. Friction. Okay, that's fine. Let's carry on. Carry on. So now we get to the part where you would think of Newton's second law. Okay, and I'm not fond of that name, but everyone calls it that, so I can't not call it that. Newton's second law, which we've already used. Actually, let's just say Newton's laws. So the first law, number one, is it's kind of weird. It's a weird law because you think, oh, well, it's the same as the second law. This says that the natural state is constant velocity. And that's a vector. So a lot of times you'll see this, an object at rest stays at rest, an object in motion stays in motion in a straight line unless acted on by a force. Really, I like to think of Newton's first law as a contradiction to the previous ideas that if you leave an object alone, it'll stop. And Newton said, no, that's not true. So then the second law is important. It says this, F net is mass times acceleration, and we're going to need to define acceleration, and I will. And if the acceleration is 0, then we get back to where we were. And then the third law says that if object A pushes on B, then B pushes on A. So it looks like this. FA on B is negative FB on A. Forces come in pairs. Okay, so in this case, we can still add up forces. We just don't have to have them equal to 0. Okay. But then what is acceleration? What is velocity? Let's talk about that. So first of all, let's go down here. I call it kinematics. And again, remember, I'm making an equation sheet. I'm not going over the whole thing. So we can define the average velocity as the change in vector position with respect to time. So normally what we'll do is if I want to have an object, x, y, I can define the location of that with a vector r. So it'll have an x and a y coordinate. Delta r would be as if this moves over here, so it's r1, and it moves over here to r2, then delta r is going to be r2 minus r1, final minus initial. So that's the average velocity. Now, if the acceleration's constant, we also have this definition for average velocity, v1 plus v2 over 2. You can actually just average that. That comes out to be very important sometimes. Now we have the definition of acceleration. It's the change in velocity with respect to time. And these are vectors, and that is kind of important. And then if you take these three definitions, average velocity is that, average velocity is that, the acceleration is that, you can get the following kinematic equations. The first one says, I'm going to write it the way I like it, and if you want to, I'll show you some alternate versions. V2 equals V1 plus A delta t. And again, this is a vector. Okay, so I'm going to put the non-vector version over here. And then the other one is R2 equals R1 plus V1 delta t plus 1/2 A delta t squared. Now there is another version that's kind of a cheat and really deals with work energy, and I'm going to show it to you. And these are the ones I like. Now, you don't have, if you set t is equal to 0, then delta t is just going to be t, right? Because it's final t minus initial t. And so you can get the following one-dimensional kinematic equations. V, sometimes I call it V final x equals V initial x plus ax t. That's where you'll see it. And then x final equals x initial plus Vx initial t plus 1/2 ax t squared. And then you have a y version, Vf y equals VIY plus AYT. And yes, if you have a free-falling object, the acceleration would be negative g. Y final equals y initial plus Vy initial t plus 1/2 AY t squared. And then we have the following, I'm going to write it in the x direction. I'll write it in the s direction. So Vf final squared is V initial squared plus 2a, I guess I should say x, delta s, where that's the distance it moved. Okay, this one really deals with work energy more, so it's a little bit weird. But these are the kinematic equations that you're going to see, and they're different versions. This is two equations. This is an x equation and a y equation, because all these have x and y components. Okay, moving right along. Along also with kinematic equations, we have another thing for acceleration. A equals delta v over delta t. But if you're moving in a circle and your velocity magnitude doesn't change, you get this. AC equals v squared over r. This is the acceleration for an object moving in a circle of radius r with a velocity v. And you can also write that as omega squared times r, where omega is the angular velocity. So omega is delta theta delta t, and that's going to be equal to, also v is equal to omega times r. So if I have an object moving in a circle of radius r with an angular velocity v, it has a linear velocity, not a vector. The magnitude is of v2. And this is for circular acceleration. Then we also have the other relationships for angular quantities. S equals r theta, A equals r alpha. So alpha is equal to delta omega over delta t. It's the angular acceleration. How fast is the angular velocity changing? And then so if I have an object moving in a circle with the changing angular velocity, then I can find the acceleration along that circle. And so you get the following angular kinematic equations also. Omega final equals omega initial plus alpha delta t. A lot of times you'll see that as just t because we're dealing with starting with t equals 0. Theta final equals theta initial plus omega initial delta t plus 1/2 alpha delta t squared. And then finally, omega final squared equals omega initial squared plus 2 alpha delta theta. And so these look a lot like kinematic equations because they essentially are. Okay, work energy. I should start a new page, but I'm not going to. Let's go up here. Work energy. The first thing is the definition of a dot product, and some textbooks focus on this and some don't. But imagine I have two vectors, A and B. I can define a vector operation called the dot product A dot B that is equal to the x component of A times the x component of B plus the x component of the y component of A times the y component of B plus the z component of A, z component of B. So you take the components, multiply them together, and then you add up those, and that is the dot product. You can also write this as A dot B equals the magnitude of A times the magnitude of B times cosine theta, where theta is the angle between A and B. And that's important for the definition of work. If you have a constant force, work equals F dot delta R, where force, F is the force applied, delta R is the displacement, and they don't have to be in the same direction. So you could write this as F delta R cosine theta, but it is a scalar value. And that gets to the work energy principle. Work is the change in energy. Depending on how you define your system, depends on what things do work and what kind of energies you have. So what kind of energies can you have? Well, you can have kinetic energy, K equals 1/2 mv squared. You can have gravitational potential energy, mgy. You can have real gravitational, ug equals negative g m1 m2 over r. That does look like the gravitational force, but doesn't have r squared, and it's a scalar. You can have spring potential energy, us is 1/2 k s squared, and again, that's that same spring constant, how stiff the spring is, and that's a stretch or compression. Then you can have other things like thermal energy, E thermal, and it depends on some don't use this a lot, is I'm going to say delta E thermal is mc delta T, where that's the change in temperature, that's the mass, and that's the specific heat constant. The specific heat capacity, I'm sorry. Okay, so that's the work energy principle. Yes, I'm flying through this. I'm looking at my notes. Next, we have the definition of power. Power, P, is defined as the rate of change of energy or the rate of change of work. Right? So how fast the energy of a system changes. And if this is in joules and that's in seconds, this would be in watts. Momentum. Momentum is defined as P is mv. And so that is a vector. And that gets to the momentum principle. F net is delta P over delta T. This is the same as Newton's second law, because if P is equal to mv, you can write this as delta mv over delta T. And if m is constant, you get m delta v over delta T, and that's the acceleration. Now, a lot of times you'll see the momentum principle like this. F net delta T equals delta P. And then they call this impulse. I don't even know why. So that's impulse and that's impulse. It's just, I don't know. I have no comment on that. That's just what it is. It is what it is. So if it's important to realize collisions, I wouldn't have this as an equation, but in collisions, if there are no external forces, internal force, then P initial equals P final. So the total momentum before the collision is equal to the total momentum after the collision. And then we have three kinds of collisions. We have inelastic, so Pi equals Pf, and, that's a vector, and V1 final equals V2 final. So if I have two objects collide, they stick together, so they have the same final velocity. Then I have elastic, and then again, Pi equals Pf, and, did I put a vector over that? That's really weird. That's fine. It's kind of funny. And the initial kinetic energy is equal to the final kinetic energy. And then we have a plane collision where Pi is equal to Pf. So in a plane collision, the momentum is conserved, kinetic energy is not conserved, but they don't stick together. Okay. Where are we now? I guess torque. We're getting there. Now I'm into the scrap paper section of the paper. So we define torque as technically it looks like this. I don't want to lie to you. It's a cross product of two vectors, but I don't know of too many algebra-based books that do it this way. They almost always say torque equals RF sine theta. So if I have some stick and I have some point about which I want to calculate the torque, and I pull on it this way, there's F. R is the vector from the point of where you want to calculate the torque to where the force is located. And then this is theta, the angle between those two. That's the torque. Now we have positive or negative torques, okay? So if the torque is a counterclockwise rotation, we would call that positive. But it doesn't really matter as long as you're consistent with yourself. So if this would rotate that way, we'd call that a positive torque. And then a clockwise torque we'll call negative. So when you add up the torques, you have to include that some could be positive rotations and some could be negative causing rotations. The torque is really important in the angular momentum principle. So let me show you that. Torque equals delta L over delta T. Technically it should be a vector, but that's fine. And L is equal to I omega. So angular momentum is all like linear momentum, except that we have angular velocity and we have this quantity I. I is the moment of inertia, where I is equal to the sum over I, mi/ri squared, which is kind of silly. But basically it says that this is a quantity that describes the resistance to changes in rotation. It depends on the mass of the object and how that's distributed. So if you have a circle rotated about the center, then I would be 1/2 the total mass times r squared. If you have a hoop like that, I, same mass, same radius, would be mr squared. Okay. If you have a sphere, I would be 2/5 mr squared. And, I don't know if you would need to memorize these things or what. I mean, I think that would be kind of cruel. I don't even use these because usually by the time we get here, we've done a lot of other stuff. So that's the angular momentum, and that's the angular momentum principle. It looks like the momentum principle, except it deals with angular momentum. You can also, since we have, if the moment of inertia is constant, then we have, we can write this as T equals I alpha, right? That looks like Newton's second law. That looks like the momentum principle, and they essentially are. And you can also have Li equals Lf, conservation of angular momentum, if there are no torques. But up here, this is really important, going back to the torque, if it's in equilibrium, then F net x equals 0, F net y equals 0, and torque net O equals 0. So the torque about any particular point that you want to pick is 0. So you can pick the point about which you want to calculate the torque. Whew, okay. I think there are other things that you may do. I glossed over work energy, right? I didn't explain how to do work energy. I just gave you the equations for it. I glossed over the momentum principle, the angular momentum principle here. Okay. You may do other things. You may do waves. You may do sound. You might do pressure. There's a whole bunch of stuff that you could do. There's a lot of stuff that I want to do. Really, for me, the main three things, when I like to stress, the main three things in the class are the momentum principle, F net equals delta P over delta T. Work energy, work is the change in energy. And then the angular momentum principle, torque net is delta L over delta T. And again, this is a scalar version. Really, it's more complicated than that. I want to tell you that there is something more out there. Okay, so those are your equation sheets for the first semester of algebra-based physics. If you need to make an equation sheet, you can use those. Hope that helps.